So I am Jimut from Siemens Department, Center for Machine Intelligence and Data Science, and my team name is Zero1. So today I will be presenting about enabling deep hierarchical image-to-image translation by transferring from GANs. So this is for I643 course project, and this was done under the guidance of P. Palamurugan. So let's start with the motivation. So from this set of images, can you guess which one is real and which ones are fake? So if we see carefully for about 30 seconds, we may find one or two examples like this one are fake, this one is fake, but actually every single image is fake. So why are we studying and creating GANs? So GAN are like creative things, so it can generate from samples, from latent vectors. So one example is creating fake images. GAN can also make this image transfer from summer to winter, or ages to photos, or day to night, or horses to zebra. It can be also used to create super resolution image like in image compression, and it can also create very realistic images by giving it some text. So now diffusion GANs and DALI and all those things have come up, which create very realistic images from descriptions. So GAN can be used for computer graphics where automation is necessary. So Yan Lee Kun described GANs as the most interesting idea in the last 10 years of machine learning. So this is the translation, how GAN used to create picture during 2014, and it has come a long way. So it is generating realistic images of human faces. Here we see a very motivating examples of StyleGAN 2 and StyleGAN 3, where we sample different images from changing the latent representation. So GAN can also be used to generate realistic, ultra-realistic face images as shown here, and we can also use the latent representation of StyleGAN 2 to generate different images from them, and this can be used in image editing purposes. So GAN also suffers from mode collapse and other stuffs, and we are not discussing due to due interest of time. So what are GANs? So the training data comes from some underlying complex high dimensional distribution P data of X, and new data can be generated by sampling from this distribution using a generator PG of X. So GAN overcame this problem by sampling from simple distribution and then learning a complex distribution to generate data. So this complex transformation is a deep neural network. So suppose this is the P data of X and this is PG of X. What the GAN does is it approximates the underlying distribution through repeated training. So this is a overview of a simple GAN. So training is done using a two-player game which comprises of a generator and a discriminator. The generator produces image that appear to be real, and the discriminator tries if it is an image, if the image is real or fake. So let's talk about the generator model. So G theta of Z where is the generator. So this part is the generator of the GAN model, where Z is the input and theta are the parameters of the model. So input is a noise vector which is sampled from PZ of Z, which can be in the normal distribution with mean 0 and variance of I. So G theta is the neural network model. So generator is the neural network model. Now let's talk about the discriminator model. So D var phi of X is the discriminator, where X is the input to the discriminator and phi are the parameters. So this is the discriminator part. So the input can come from the data, so real data, or the generated data, this one, and D phi is also a neural network. So the discriminator outputs a score between 0 and 1. So this is a probability of an image being real or fake, which means if it is outputting 0, then it is fake, and if it is outputting 1, then it is real. Now let's talk about the generator objective. So now the things get a bit theoretical here. So generator wants its output g theta to be classified as real. Therefore, it wants to maximize the log of d var phi of g theta of z, or minimize log of 1 minus d var phi of g theta of z. So we want the generator to do this task for all possible values of z sampled from the distribution pz of z. Therefore, the objective becomes this equation. So min of theta, we integrate pz of z, and log of 1 minus d var phi of g, this is the generator content. Or we can also minimize the expectation of this term. Now we will talk about the discriminator objective. So the discriminator should assign high score to real images, which means we can maximize the expected where x belongs to p data, and log of d var phi of x, which is the discriminator. So we need to maximize this, and we should assign low score to generated images, like this is done by minimizing var phi u of z belongs to pz, this term, or maximizing 1 minus this term. So the combining discriminator objective function can be written as this one and this one. So this one and this one. So now we will talk about the combined objective function. So the generator and discriminator's objective combined yields a min-max problem. So the first expectation is independent of theta, and the second expectation is minimized with respect to theta and maximized with respect to var phi. Hence the generator wants to minimize the second term, while the discriminator wants to maximize it. Now there is a problem in gradient. So early on training, it is more likely that d of var phi g theta of z tends to 0, as the generator has not learned much, and it is easy for the discriminator to identify the difference between real and fake samples. In such a situation, the gradient of log of 1 minus d var phi of g theta of z is close to 0. The generator does not learn much in the beginning, and there is little change in theta. So now we need to modify the objective. So originally we were performing minimization with respect to the generator parameters theta, that is this term. Now we use a modified version of the above minimization. So we minimize z sample from pz of z minus log of this term, which is maximizing this term. So we modify the objective function to this term. So this has a large gradient when d var phi of g theta z tends to 0. This also enables the generator to learn more in the early training period. Now this is the algorithm for training of GANs. So we sample mini batch of m noise samples from noise prior, and we sample m examples from data generating distribution p data of x, and we update the discriminator by ascending its stochastic gradient using this. And we sample a mini batch of m noise samples from noise prior and update the generator by descending its stochastic gradient. So it is playing a zero-sum game by repeatedly getting better and better discriminator as well as the generator. So this is the objective. This is a min-max problem, and we can rewrite the objective function as this. It's a simple integration. Now the revive objective function can be written as this min-max problem, which is this, and we have done a few mathematical proof and theoretical analysis. So what we have found is that the global minima, so here we are computing the global minima of c of g theta. It is achieved if and only if p of g equal to p of data. So here what we are doing is, when p of generator equal to p of data, the training will kind of tend to flatten. Now we will move on to what we are working on, which was proposed for the course. So we will be talking about DeepI2I, image to image translation. So let's talk about the summary. So image to image translation is used in the field of computer graphics, especially in movie industry. So traditionally this is labor intensive process, and the proposed technique can be applied to automatic translation of faces or objects. So I2I translation shows inferior performance when the translation between classes require large shape changes. So we need to learn the model by leveraging hierarchical features, that is structural information contained in the shallow layers and semantic information extracted from the deep layers. So the authors have implemented a novel transfer learning method by transferring knowledge from pre-trained GANs, enabling learning on small dataset, which was not possible before. So they leverage the discriminator of a pre-trained GAN to initialize the encoder and discriminator, and leverage the pre-trained generator to initialize the generator of their model. So they have also introduced adapter network to address the alignment problem between encoder and decoder when using knowledge transfer. So they are the first to do image to image translation over 1000 classes in animal faces, birds and food dataset. They qualitatively and quantitatively showed that transfer learning significantly improves the performance of image to image translation for small datasets, which wasn't done before. So this is the architecture of their network. So the left one is the conditional GAN, and they are basing their network on big GAN architecture, which contains generator phi and the discriminator psi. And their method consists of 4 terms, that is the encoder part, the adapter part, the generator part, and the discriminator part. So what this adapter network does is it takes feature from several of these layers in the encoder, and it seamlessly integrates it to the decoder for changing getting good semantically and logically corrected images. So it wasn't possible before to do translation on data which have much changes in geometry. So what the author proposed was they have used multi-scale feature maps to integrate this, since we need structural informations which were contained in the shallow layers and semantic information which are extracted from the deeper layers. So generally image to image translation technique have 2 to 3 layer maximum 2 layers of down convolution and up convolution, which were not able to extract the semantic information, just structural information, since they were not performing good when there are large shape changes in the images. But this work does really good in addressing those issues from the previous related work. So one of my favorite results is when they are inputting a beer, it can be used to change the shape and structure of the face to any of the dog or bull or setter or sheepdog, etc. It can also happen for if the image is input as food samples. So we can translate from one food samples to other, and so the face data, the animal face dataset have quite good results, and they have also tested their input on different on unseen images. So they were not training on human faces, but in here they have given a human face and they were projecting the latent space to check if their images are good or not. So the input image is mapped to 8 animal faces with StarGAN and DeepI2I. So here are the references and here are the acknowledgements. So thank you. Well, one thing I forgot to mention is that GANs are not the only architectures which can generate samples. We can also generate samples using variational autoencoder. So here is a simple test that I have done previously, so this is not written in PyTorch. I have used variational autoencoder, simple variational autoencoder, and we have used a latent space of 200 to generate face images and from Celibay dataset, and also we can use this model to interpolate between two latent vectors, and this will be having a similar effect as the translation GAN, image to image translation GAN, that the current authors have proposed. So this was done way back. So this is somewhat related, not fully related, but this is somewhat related to the project.